Hello everyone and welcome. In this video I'm going to show you how to run a Shapiro-Wilk test, so test the normality, how to get a QQ plot, how to do a test a Levene, and how to do a box plot, which are all assumptions that you most normally need for some statistical test, such as the ANOVA or the pair sample t-test. So the dataset I'm going to use is from a specific package called mass. But if you are enrolled for the module MM1F28 and you have access to Blackboard, you should be able to download it from there. So I'm going to show you first how you get the dataset from Blackboard, and I'm going to show you how you can download it from or use it from the mass package. So if you go into Blackboard and then you go to Learning Materials and then Session 2 and then Workshop, that's the melanoma. That's a file you need. If you click on it, you will download it, and then what you have to do is just move it into the folder where you've saved all the other data sets. So I have it here, okay? Otherwise, what you need to do is first set your working directory. So you would have to session, set working directory, choose directory, and then go to where you have the folder where you have saved your melanoma file. So this is my folder from the desktop. Click open, and then we'll set your working directory. And then if you go into files, you will see that you have the melanoma and the roger.csv file. Or what you could do is use the console or type in the script, install the package called mass, and then load the package, and then assign the melanoma dataset from within the package mass to a variable, and then store into the environment here. So you would have to type install.packages and then quotation mark, capital M, capital A, double capital S, and that is to install the package mass. You see, if I put a hashtag before a code, before some words, that whole line becomes green, and that because it's green is commented out, so RStudio knows that this is not code, it's just some information that I'm putting there for me so I remember what I'm doing. So the first step is to install the package mass. The second step is to load the mass package. And to do so, we can do library open round brackets MASS. Make sure that everything is capitalized, because that's case sensitive. As to this case sensitive, so we need to have this. So if I run the first line, and I can run the first line either by selecting it and go to run, or I could press Control Enter or Command Enter, and that would run it. So you can see that when I run the first line, I get this red code. This red code is not an error, it's just telling me what's happening, and it's downloading the mass package. And then I have the black font where it tells me where the package has been downloaded. That's fine. You only need to install the package once, okay? You don't have to install it all the time. What you need to do all the time is run this command, okay? So every time you want to access a package. So if I press Command and Enter, or Control and Enter if you're using a Windows computer, you will see that in the console, this is loaded and nothing appears. So it's perfect. I've loaded a mass package, and now I can access the melanoma. So if I want to save it, I can put into data, and then instead of using the equal sign, which will be probably familiar with you if you're using Python, we need to use this different symbol in R, which is smaller than and then an hyphen, okay? And then we put melanoma with capital L. Then you will see that there is auto-completion coming up. You can click on it. It means that you're storing what is in this variable, which is the melanoma. So the data set is going to be stored in this variable called data. Okay. So if I run this line, then I will see that in the global environment, in the environment now, I have something under the row data, and it's called data. That's the name I chose. And it's 205 observation of 7 variables. If I click on it, I will see this. That looks like an Excel file, more or less, right? So we have 205 rows. That's one, the observation, 205 observation means. And we have 7 different columns. So time, status, sex, age, year, thickness, ulcer, okay? That's the 7 variables. So this one way of doing so. The other way would be to download the file for Blackboard, save it into the working directory, and load it using rcommander. I'm going to show you how to do that as well. So the next step is to load the rcommander package. So you need to have it installed. If you haven't installed it, look at the previous videos when I explain how to install the rcommander package. We can type now library. You can type it in the console or in the script, whatever you prefer. Capital R CMDR. So if you're typing in the console, you don't need to do command enter. Just enter is fine. But if you have typed this in the script, then you need to do command enter. Okay. Press enter, and then you see that we have all these red lines. They're not error messages. It's just RStudio telling us what's happening under the hood. So you're loading at the packages at the same time, and now the classic interface of rcommander will appear. There it is. So now if you have decided to go down this route, so install the mass package and get the melanoma dataset from the mass package, what you need to do now is click on dataset and select data, okay, and press OK. If you do so now, you can view the dataset, and that's dataset you have uploaded, okay. If you have decided to download the CSV file from Blackboard, then you need to do another step. You need to do something different, okay? So you need to go into data, import data, and then remember, even though it's a CSV file and normally is open with Excel, we don't want this option. We want the first option, okay? From text file. Remember to tick commas, okay? Because what we're using is a CSV file, so comma separated values. That's why we're using commas. Press OK, and then click on melanoma, okay? If melanoma doesn't appear here, it's because either you haven't downloaded it, so you need to do that, or because you don't have changed the working directory. So you need to find, using this interface, you will need to find where you have stored, in which folder you have stored the melanoma. In my case, it's in desktop, and then mm1f28, and there it is. Okay, or you can close here, go back here, do session, set working directory, set the working directory first, and then trying to see if you can do data, import data, and find it, and find the melanoma file from the new working directory we just set. Make sure that you always take the commas. Press OK. We click on melanoma, we press open, and now we have dataset, which is the name that rcommander has given to the dataset, to the melanoma file. Good. So if you look at the view dataset, is the same as before. Okay. So now briefly to talk about this dataset, what we can do is have a look here. So you need to do double quotation mark if you are, or to the quotation mark if you're interested in see what the melanoma, what the function is. We need to look at mass melanoma. If you haven't installed the mass package, this will not be available to you. But I'm just doing that so you know what we're talking about. So the melanoma data frame has a data from on 205 patients in Denmark with malignant melanoma. Okay. So time is survival, time in days, possibly censored. Status is 1 died from melanoma, 2 alive, 3 dead from other causes. Sex, 1 is male, 0 is female. Age is age in years. Year is age of operation. Thickness is tumor thickness in millimeters, and ulcer is 1 present, 0 absence. Not the greatest data set. I know it's not very cheerful, but it serves as a purpose just to show you how you analyze some data. So bear with me, even if it's not the most nice data set you will ever encounter. So what we want to do, we want to check if our variable called thickness is normally distributed, okay? And then we want to see if there is a difference on thickness depending on sex, so male versus females. So we know that 1 is male and 0 is females, right? So what we want to do first is recode sex so that rcommander knows there is a factor variable, so it's not continuous, right? So to do so, we need to go into data, active dataset, manage variables in active dataset, convert numeric variables to factors, okay? and then we can select sex, and we can supply level names. Okay, if you want to, you can just tick use numbers, but I'd like to do supply level names so we can specify 1 is male and 0 is female. So we click OK, we click yes again. So 0 is female and 1 is male, and then we press OK. And now, can you see? Let me do it again. If you click on view dataset, where we used to have ones, now we have male. Where we used to have zeros, we have females. Okay, so now we have the two groups. Cool. So what we want to do next is to check if our dependent variable, so thickness, is normally distributed. In order to do so, we're going to run Shapiro-Wilk test. Okay, so we go into statistics, summaries, test of normality. We make sure the Shapiro-Wilk is selected, and then we click on thickness. After we've done that, we press OK. And here we have in the console the output. Now, if you don't like this notation, this is scientific notation. It basically tells you have 2 by 2.2 is as 16 zeros before it. So I don't know if that makes sense. Let me show you. So this is 2 by 2, right? And then if I do 2 by 2 e to the power of -1, it becomes 0.22. So 2.2 e to the power of -2, it becomes 0.022, 0.022, and so forth. So unfortunately, it stops at 9, right? So if I try to do 10, it will give me the same result. So if I try to do 16, it will give me the same result. If you're not happy with that, there is something you can do, you can change, and I'll do it in the script. So you can type options sci pen equal 999, and this turn off scientific notation. If I run it, and then I go again, statistics, summaries, test of normality, everything as before, so as I wanted, press OK. Now I will have my result with the 16 zeros before the 22. Okay, all this to say that that's how you get the turn off the scientific notation, but the result doesn't change. So that's the Shapiro-Wilk normality test. That's the W value. Okay, but what we're interested in is the p-value, and we would like to have a p-value bigger than 0.05 in order for the variable thickness to be normally distributed. In this case, the p-value is smaller than 0.05, clearly. So the variable is not normally distributed, which is bad news. Okay. So what we can do is also we can check the QQ plot to see what our distribution is. So if we go into graphs, then we can do quantile comparison plot and select thickness. You can have a look at options, but we're happy with the default, and then we can press OK. And there it is. There should appear a plot for you. Okay, so that's the QQ plot for the thickness, and then you can see that there is a clear deviation from normality. So in order to see what a normal variable, or a variable that follows the normal distribution would look like, you would have all the circles more or less aligned on this blue diagonal line, or at least within this area. Okay, so you can see that at both ends we have a clear deviation from the blue diagonal line, so normality cannot be assumed. Okay, we can close this. The next step we want to do is to check for the homogeneity of variance. In order to do so, we need to do the Levene test. Okay, so if you go into statistics, variances, Levene's test, sex needs to be a factors. If sex doesn't appear here, that's because you haven't recorded from numeric to factor, so you need to go back and do so. We've done it, so that's perfect, and we just have to select thickness as our response variable. We're happy with median, and we press OK, and that's the output that we will get. So we need to look at this row, and we need to look at the p-value. Again, for the homogeneity of variance, we would like the p-value to be bigger than 0.05 so that homogeneity can be assumed. In this case, you can see that the p-value is smaller than 0.05, so homogeneity has been violated. Okay. In order to visually inspect this, we can do box plots. Okay. So if we do into graphs and then box plot, we need to check plot by groups, select sex, press OK, select thickness. We don't have to look at the options. We're happy the way they are, and then we press OK. And there is the box plot. And you can see that the height of the two boxes are very different, right? So clearly there is a violation of homogeneity of variance. Now, because both the assumption of normality and the assumption of homogeneity of variance have been violated, we need to run a non-parametric alternative of the t-test. So in order to do so, we go into statistics, non-parametric test, and then two-sample Wilcoxon test, the first option. That's what we want. We click on it. Sex is our groups, and then the response variable is thickness. We can look into option. We don't have a direction for our hypothesis, so we can pick two-sided. If you have a direction for your hypothesis, so you think that the tumor thickness is going to be bigger for females or bigger for males, you need to pick either difference smaller than 0 or bigger than 0. But we don't have any, so we're happy with a two-tailed hypothesis, and we press OK. And there you can see the Wilcoxon-rank sum test. Okay. Here we can see the value for the Wilcoxon and the p-value. Now, for the Wilcoxon-rank sum test, we would like the p-value to be smaller than 0.05 for it to be significant. What I mean is, in order to see that there is a significant difference in tumor thickness between males and females, the p-value for this test needs to be smaller than 0.05. In this case, you can see that the p-value is smaller than 0.05, so we can say that there is a significant difference between tumor thickness, males versus female. Okay. To further inspect, we can do a plot of means. Okay. So if we go into graphs and then plot of means, sex is our factor, thickness is the response variable. This time we go to option and we change something. The other times we didn't change anything, but this time we will. We take on confidence intervals, okay, as error bars. We leave the rest as it is. We go back to the data, press OK, and then we'll have our plot. And here you can see that the thickness, so on the y-axis you have the mean of thickness, on the x-axis you have the two groups, you have females and male, and you can see that the male, that's dot, is the average. The average of male is higher than the average of females, and even though the confidence interval, they overlap, we have a significant difference between the two. Okay. So as a recap, what we did today was, first of all, install a package, mass. I don't know if you ever used it, but I showed you how to install a package, how to load it, how to get a variable, a data set from a package and put it into a variable, a new variable, how to turn off the scientific notation as well. Then I showed you how to change the working directory, how to load our commander, how to get a data set from the environment into our commander, or how to load a CSV file into our commander so it becomes a data variable in our environment. And then we done some statistic analysis. We did, first of all, the Shapiro-Wilk test, right, which is here. And we say that the p-value needs to be bigger than 0.05 for the assumption of normality to be met. Then we look at the QQ plot to see the distribution from a qualitative point of view. Next step was to check the homogeneity of variance, and we did the Levene's test to begin with. And we noticed that the p-value was smaller than 0.05, so homogeneity of variance assumption was not met, which means that the p-value needs to be bigger than 0.05 in the Levene's test for the assumption of homogeneity of variance to be met, to be true. And we also look at the box plot to visually inspect that. Now, because both the assumption of normality and the assumption of homogeneity of variance were not met, we run a non-parametric alternative test, which is a Wilcoxon-rank sum test. And we said that the p-value needs to be smaller than 0.05 for the test to be significant, and that was our case. So we had a significant difference between males and female regarding tumor thickness. And then the last thing we did was do the plot of means to visually inspect the difference between the two groups. Okay, so I hope this was helpful. If you have any doubt or something is not clear, please drop a comment under the video or send me an email. Thank you. Bye-bye.